Good morning, good afternoon, good evening. Welcome back to Chapter 5. We just got done talking about ATP. We got done talking about anabolic and catabolic reactions. Now we're going to move on and talk about the role of enzymes in these reactions. In the chemistry chapter, we talked about how proteins are tools and that enzymes are special tools. A tool allows you to accomplish a job you would not be able to do otherwise. If you didn't have a hammer, you couldn't drive a nail. If you didn't have a screwdriver, you couldn't unscrew the bolt. You've got to have a tool to accomplish that job, and enzymes are biological tools. The way enzymes work. In chemistry class, we say that an enzyme makes reactions happen faster, and that's great. Woohoo! This isn't chemistry, this is biology. In biology, it means more than that. It's not simply just how fast do the reactions happen. It really is whether they can happen or not. When we talked about anabolic reactions, we talked about building up reactions. We said you have to pump energy into them to make them go. In chemistry class, if I have a low energy reactant that I've got to pump energy into to make the reaction happen, I just put a Bunsen burner under it. I literally light a flame under it, and I heat it up. And then once you've heated it up enough, bam, we start the reaction, and now the reaction will continue until I end up with my products. The problem is, can I just heat your body up? Your body runs at about 100 degrees, 98.6, and you can't make it run any faster than that. You can't make it run any hotter than that normally. Yeah, you can have a fever, but you don't want to have a fever all the time. So what happens if the reaction that I need to accomplish, what happens if it takes place at 150 degrees? And the answer is tough. You can't get up to 150 degrees, then that reaction just doesn't happen. What the enzyme does is the enzyme lowers what we call E sub A. E sub A stands for the energy of activation, or sometimes called activation energy. What it does is it lowers how much energy I have to put into the reaction to make it go. Notice, still the same amount of energy in the reactant, still the same amount of energy in the products, but all it does is it lowers the temperature the reaction takes place at. So if I can bring it from 150 degrees down to 98.6, well, now I can do this reaction in my body. That's what enzymes do. Enzymes lower how much energy it takes to make the reaction happen, and therefore they make it so these reactions can take place inside our bodies. We have 1,000 different reactions that have to take place in our body, and therefore we have 1,000 different enzymes who lower the energy of activation of any given reaction to make it so that it can happen in our body. Without these enzymes, those reactions just don't happen. And, well, so what? Big deal if they don't happen. Big deal if they don't happen is you die. All of these reactions you need to stay alive, and if they don't happen, you are just dead. Enzymes, they lower the energy of activation. Yeah, they make the reaction happen faster. No, really what they do is they make the reaction happen. End of story. They just make the reaction happen. An enzyme has a very specific place on it where what we call the substrate binds to it. And a really good example of this would be like a wrench, like an open-end wrench. I've got a special pocket on that wrench where something special binds to it. And the special thing that binds to it is the head of the bolt. The head of the bolt is the substrate, and the box of the box-end wrench is what attaches to the substrate. Now once the two have joined together, I can now do the job. It's a bit more complicated than just a wrench and a bolt. It's probably more accurate than like a key in a lock, all right, because of how specific the connection is, because of how specific the shape has to be. The key is the substrate, the lock is the active site, and that really is a bit more accurate. Once I have bound the substrate to the active site, now the enzyme will do its job. And it really depends on the enzyme as to what it does. It might break something off, it might add something to it. But once the key has gone in the lock, once the substrate has attached to the active site on the enzyme, now the enzyme will do its job, and it depends on the enzyme as to what it does. As we said, it has a very specific shape to do its job. Just like a lock has a very specific shape, a key has a very specific shape, and only by matching the two of them together can the job be accomplished. When the substrate attaches to the enzyme, that's when now the tool can do its job. The enzyme can do its job. Here we see an enzyme with its very specific active site. Here is my substrate. Here's the thing that connects to, that binds to my very specific active site on my enzyme. Once my very specific substrate has attached to my active site, now the enzyme will do its job. And its job, in this case, its job is to break that bond right there. This is sucrose. This is what you put in your sweet tea. Sucrose is two separate monosaccharides, glucose and fructose, bonded to each other. When I put sucrose into the active site on its enzyme, look at this enzyme's name. Sucrase. How do I know this is a sugar? Because it ends in OSE. Anything that ends in OSE is a sugar. Notice how this has a very similar name, but it ends in ASE. ASE, guess what that means? It means enzyme. Anything that ends in ASE means enzyme. So sucrase is specifically and if you have an enzyme that has a very similar name to some other molecule, chances are it works on that molecule. So sucrase does what to sucrose? Sucrase breaks down sucrose. How does it break it down? It breaks that bond right there. When you break that bond right there, remember, dehydration synthesis is what I use to put them together. Hydrolysis is what I use to break them apart. I use a water molecule to break these two apart. I've now separated the sucrose from the fructose. And now once I've separated the sucrose from the fructose, they pop out of the active site because they don't fit anymore. This is the shape they have to be in to fit in the site. They're no longer in that shape. Now that they're not in that shape, they don't fit, so they pop out. And now I can use my enzyme again. Just like a key in a lock, I can use that key over and over again to open that lock. This tool can be used over and over again. This is how enzymes do their job. They've got a special slot where something special binds. Once it binds to the special slot, then the enzyme will do its job. And again, it depends on the enzyme. It might be breaking something. There's another enzyme that links them together. All right? Different enzymes have different jobs, just like different tools have different jobs. If this is my active site on my enzyme, if my key's job is to open a lock, then it suggests that that's the only thing that will go in that lock. But is that true? What if I were to take a bunch of toothpicks and jam them in the lock? What have I now just done to that lock? And the answer is I've ruined it. The toothpick is not made to go in the lock, but it does just happen to fit. A competitive inhibitor is a molecule that prevents an enzyme from doing its job by attaching to the active site. The toothpick jamming in the lock prevents the key from attaching to the lock. Competitive inhibitor. A competitive inhibitor attaches to the active site on the enzyme. And most of the time, it's not supposed to. It just accidentally fits. There is also something called non-competitive inhibition. A non-competitive inhibitor attaches to somewhere else on the enzyme and causes the active site to change shape. The result is the same, and that is that the reaction doesn't happen because the substrate can't bind to the active site. In this case, it's because the active site is blocked. In this case, it's because the active site has changed shape. This is the non-competitive inhibitor. This is the competitive inhibitor. This is how you can influence how enzymes operate. I can start or stop an enzyme by adding an inhibitor, a competitive or non-competitive inhibitor. Lots of enzymes operate off of feedback inhibition. Feedback inhibition says that if the product of the pathway builds up, it will shut the pathway down. Example, if I have a shovel factory what is my product? My product is shovels. What happens after I finish making this shovel? I take it to my warehouse, and I find that I don't have anywhere to put it because my warehouse is jam-packed full of shovels. Should I keep running my factory? Should I keep making more shovels if I don't have anywhere to store the ones I'm making now? And the answer is no. I shouldn't be making more shovels. What do I need to do before I make any more? What I need to do is sell the ones that I have. I got to get rid of some stock before I can make more. The product of the pathway inhibits the pathway. Feedback inhibition. Most of your enzymes operate off of feedback inhibition. If that glucose and sucrose build up because sucrase has been really, really active, and the glucose and the sucrose aren't being destroyed, they will inhibit the operation of the sucrase to prevent it from cutting up more sucrose. Feedback inhibition. Here's my starting molecule, the thing that I break down, and it follows a whole bunch of reactions until I end up with a product. Often, if that product starts to build up, it will inhibit the enzyme that does the initial breaking down of the product. If I've got too much of the product, then I should stop doing the reaction. Feedback inhibition. This is called negative feedback, where the product of the pathway inhibits the pathway. And most of your enzymes work off of this feedback inhibition. If I've got too much of the product, then I don't need to run the reaction anymore. I need to stop it. Lots of medicines work off of enzyme inhibition. Ibuprofen will inhibit an enzyme necessary for the sensation of pain. Some blood pressure medicines are feedback inhibitors. Some antidepressants are enzyme inhibitors. Lots of antibiotics inhibit enzymes. Some protease inhibitors are used to fight HIV. Lots of poisons inhibit enzymes. Lots of medicines are enzyme inhibitors. And in a way, you could say that lots of medicines are poisons. Now stop before I go any further, don't freak out. What I mean is, if you take a little bit of it, it's good because it helps you. But what happens if you take a lot of any medicine? If you take a lot of any medicine, you can get sick because you've now taken way too much of this thing. Lots of medicines are enzyme inhibitors, and if you inhibit the enzyme a little bit, if that enzyme is overactive, it can make you feel better. But if you inhibit it a lot, you can get really sick because you take too much of it. See you in Chapter 6.